Yeah, thank you. Okay, so this is the second and last lecture. So what I wanted to do first is to briefly review what we saw yesterday. So quickly go through the slides that I showed yesterday. And well, if you had some question that you didn't ask yesterday, or there was something that you missed, some concept that you didn't quite get, it's your opportunity now to ask. Okay, so yesterday, well, as I said, there are three parts to these lectures, and I started by introducing what are the observables that we are interested in, the cosmological correlators, and why are we interested in them. So then I started by telling you that cosmology is all about measuring correlation functions in in late time structure, right? Correlations like this, and that by using the evolution equations and the physics that we know about the universe, we can trace them back to correlations in this surface of reheating, which is the surface of the end of inflation, basically. And this gives us a window into the early universe, into the inflationary universe, because the correlations there were created, were sourced by the dynamics of inflation, basically, by quantum fields and quantum interactions in the inflationary spacetime. And this is important because inflation was very energetic, so we basically have a cosmological collider with energies that are very, very high. Yeah, and then what else? Yeah, well, so I said that those were the observables of interest, but that we would work with a more primitive object, which is this wave function of the universe, which is actually a wave functional, which computes these correlators. And all of the information about this wave function of the universe is contained in these wave function coefficients, and those are the actual objects that we are going to try to compute. And they are related to the correlators, to the actual cosmological correlators. In perturbation theory, they are related in this very, well, more or less simple way. Okay, I told you that there is a diagrammatic way of computing these wave function coefficients by assigning propagators to legs in diagrams, etc. And I showed a very simple example, but in general, this, especially for the Sitter spacetime, this is very hard. Integrals, the computations are very, very hard. So we want some other method to help us doing these computations. And that's where I talked about the bootstrap. The bootstrap is basically this philosophy of trying to get observables in field theory from first principles directly, skipping the step of evolution, solving equations, solving the time evolution, etc., etc. Well, I tried to argue that this was very successful in the case of scattering amplitudes. It has also been very successful in the case of CFTs, the famous conformal bootstrap. So we want to apply it to these cosmological correlators, to these wave function coefficients. So in other words, we want to just solve these objects directly from physical principles at the boundary where they reside, without the need to do the time integrals or whatever, the time evolution in the bulk spacetime. Yeah, and this has the two advantages. One that I already mentioned, that calculations will be more simple, and the more conceptual advantage that it focuses on observables and it makes more transparent the relation between the physical principles and the actual structure of the observables. Okay. Yeah, and then I got to the final, but more technical and more important, let's say, part, which is the part in which I'm going to explain all of the different methods or techniques that we use. And I already told you that one of the things that we leverage in order to fix these wave function coefficients, these objects, is the symmetries of the spacetime. So in particular, well, we basically work with the de Sitter or quasi-de Sitter spacetime, and the de Sitter isometries in the boundary where we are computing our correlators become conformal symmetries. And this means that these wave function coefficients that we are interested in are actually well, have the same symmetries, behave in the same way as correlators of a CFT. And then the primary fields that enter those correlators are the dual fields to the fields of the Sitter or whatever spacetime. And they have a scaling dimension which is related to the mass of the field in the Sitter. And then, well, in this way you can relate these correlators, conformal correlators, to the correlators that are observationally interesting. And as I said, we are focusing on computing this, so we are focusing on computing these conformal correlators. So, you know, there are these two types of correlators: the ones that are observationally interesting, and the ones which are correlators of their dual fields, their dual correlators. And the ones we actually compute are those, the latter. And then we can use them to obtain the physically interesting one. Well, the reason we do it this way is because many of the things that I will say, of the conditions or constraints that I will talk about, are more easily imposed on these correlators instead of this. And also because these correlators actually contain more information than the physical ones. So, okay, so this is what I said. I don't know if I'm forgetting. Yeah, so then, well, these symmetries constrain the correlators very much. And one strategy that you can find in these papers and also in these lectures is to try to solve them directly. But I said that in these lectures, I will try to be complementary, and I will try to show you other strategies that we have used, which are not to directly solve the conformal word identities. And these methods that I will be focusing on are powerful for wave function coefficients which are meromorphic, so which only have poles. They don't have branch cuts, etc. This happens for wave function coefficients of fields which are massless, basically, even if they have spin. So that means that we will focus on wave function coefficients that involve massless fields, gravitons, so spin 2 massless, and spin 1 massless, which could be a gluon or a photon, something like that, which is not observationally interesting because those correlations of spin 1 fields do not survive to be observable in the late times. But anyway, conceptually they give us a lot of information, so it's still very interesting to study them. Okay, so the next thing I'm going to talk about in this list of things is the singularities of the correlators, and this is actually very, very important. It's very important to know the singularity structure of the correlators. It gives us a lot of handle. And you know, this is a list of cosmological bootstrap methods or principles. And there are kind of two steps to the cosmological bootstrap. The first step is to try to derive the consequences of these principles on the wave function coefficients. And for that, we usually, go to the bulk, or we usually study properties of the propagators, etc., to derive this. And then the second step is to use those conditions that we derive to actually fix and compute the wave function coefficients. So I will try to show a bit of both. I will try to derive conditions. For example, what does unitarity imply for the wave function coefficients, and on a second step, I will try to give you an example of how to use those conditions to actually compute them or fix them. Anyway, let's go. Yeah, so singularities. So it's very important, the fact that these wave function coefficients have singularities in certain kinematical limits. Okay, so these are functions of the kinematics of the momenta, and in certain limits they are singular. So here I have a scattering amplitude. Okay, so it's not a wave function coefficient. This is a scattering amplitude, and here I have a corresponding wave function coefficient. Let me start with the scattering amplitude, and let me kind of show explicitly how one computes this. So it's a very simple scattering amplitude, 3 points. So here I have the vertex coefficient. This is just usual Feynman rules, right? Here I am integrating over the time at which this interaction takes place, and then I have to multiply by the let's say by the, in the case of the wave function coefficient, this would be the back to boundary propagators. In this case, it's just plain waves associated to the fact that I am Fourier transforming this scattering amplitude to the time variable, and this K is actually big K, capital K. Make it more clear, and it's the sum of the three energies of the momenta of these three legs. And if you do this integral, well, you get the vertex factor, and then delta function of this capital K. Okay. So this delta function is imposing energy conservation. Of course, there is also a delta function of the spatial momenta, but well, all of those delta function of spatial momenta, I am omitting them in all these lectures. They are always there, okay, because we have translation invariance. But in this case, in the case of scattering amplitudes, we also have time translation invariance, okay, and that implies energy conservation. So, you know, that's why we have the delta function. Now, in the case of the wave function coefficients, I already told you what were the diagrammatic rules. You also have to multiply with the vertex factor, and then also have to integrate this point in time, multiply with the back to boundary propagators of the three legs, which gives you that exponential. But this time, notice that the limits of the integral are different. We are integrating from minus infinity, so from far back in time, until 0, which is the moment in time to which this surface corresponds. And this changes the result, the fact that we are using the different limits. So we're gonna get this integral. If you remember, we did it yesterday. We computed the same thing. And here the limits. And remember that we had to add a tiny real part to the exponential to regulate it in the far past. Okay, so now this is going to be this. We already calculated it yesterday, as I said. So yeah, so what is happening here? So you see that because we are fixing, we are doing the computation of this wave function coefficient at a specific time, at a specific moment in time, we are breaking time translation invariance. Okay, we no longer have in states and out states that go to past infinity, from past infinity to future infinity. Now we have something coming from past infinity, which we compute at a specific time slice. So we are breaking time translation invariance, and we lose energy conservation. And instead of having this energy conservation, now we have a singularity of the total energy, the sum of the three energies. And the way that you can understand this singularity in more mathematical terms, well, this singularity comes from the region of the integral that is in the far past. Okay, so from this region of the integration, and the reason is that if k is 0, so if the total, if the sum of the three energies is 0, then this exponential is not here; it's just a 1. So we have an infinity. This integral is infinity because we have, we are integrating over an infinity amount of time, infinite amount of time. So that is what it means. And the very important thing about this is that the coefficient of this singularity, this v of k, this is actually the scattering amplitude, right? So the scattering amplitude is this, up to, of course, up to the delta function. So in other words, this is telling us that the limit of this wave function coefficient when the total energy goes to 0 is basically the scattering amplitude over the total energy that we are taking to 0. So it's a singularity whose coefficient is the scattering amplitude. And again, you can understand this a bit, well, heuristically from this picture, because we are, the singularity comes from dragging this interaction very to the very far past, and at that point, in that limit, let's say the interaction is not noticing, or the fields, let's say, do not notice the future boundary, so they feel the same as if they were just in usual flat space. The limit, let's say, becomes equivalent to computing a scattering amplitude, and that's why, well, intuitively, that is why this coefficient is the scattering amplitude. Okay, so this is a very important property of
something about it.
Yes.
In this case, actually, as you said, the psi tree, so the coefficient of wave function, should be a sum of loops and etc., right?
Mm-hmm.
In this case, you are considering just the tree level. So yeah. This is just for the tree level, or for the entire sum when you are summing for the loops and etc.
This is true for the entire sum.
Okay.
Yeah. You should get also the corresponding. You should always get, when you go to this limit, you should always get the corresponding flat space scattering amplitude as a coefficient. In this case, the corresponding one is this scattering amplitude. If you have a more complicated diagram, then, well, the scattering amplitude that corresponds to that more complicated diagram. Yeah. Yes. Okay, so, well, a couple of references for this total energy singularity are these. So this was, I think this was first noticed in this paper by Pimentel and Maldacena, and then Raju also noticed it for ADS correlators. And well, and this is not only true for the 3-point wave function coefficient. This is true for any wave function coefficient, so also for more complex diagrams. So I have a more complex diagram here. In this case, you can see, well, this is just a random, well, whatever, tree-level diagram. Okay, so you can insert here inside as many propagators as you want, as many lines as you want, and this is any number of lines flowing to the boundary. And this KR is the sum of the energies of all these lines. KL is the sum of the energies of all these lines. And why is this internal energy? So what I'm going to try to prove is that if this property is true for the diagram here, then it's also true for this whole diagram. So a recursive relation, let's say. And from this recursive relation, we will prove it for all tree-level diagrams. So this diagram here, let's call it psi n. This is given by this expression. We have to integrate over the right vertex, the right time. KR is the sum of all of the energies flowing there. And this blob here just represents any number of propagators that account for the graph that we have in that blob. And then the other vertex. And here we have the bulk-to-bulk propagator corresponding to that internal line that I draw here in blue. So, okay, let me copy this to the next slide. We can now substitute this bulk-to-bulk propagator, and I will not. By the way, I'm now working in flat space. Okay, so I'm computing this wave function coefficient in flat space just because, as you know, it's much more simple, and I am assuming that all of these lines are massless scalars, so just the simplest case. So I substitute this bulk-to-bulk propagator, and I'm going to use this frequency representation of the bulk-to-bulk propagator, which is not the expression that I showed you yesterday. This is an alternative representation, which is going to be more useful for this particular computation. But you can convince yourself in 5 minutes that this representation is equivalent to the expression that I gave you yesterday. TL plus TR. Okay. Hope you can see it's not too small. Oh, with an eye, by the way. Okay, so let me see. Nothing changes here. I'm just going to copy. And here, what we are going to do now is we're going to form this time integral first. We have done these time integrals already a number of times, so shouldn't be hard. I will just write the final result. Okay. Very good. So this is the result of the integral over t left. It's very easy to do because you just have to take out the common factor that involves t left, add it to this exponential, and that is going to give you this 1 over that coefficient. Okay, now we can do this integral over the frequencies with some complex analysis, picking some poles and so on. And the result is going to be this. By the way, let me say I'm using Y for this internal energy, okay? So for the magnitude of the moment of the sum of momenta that run in this line. This is different to what I used yesterday. Yesterday I was using S because it was an kind of S channel diagram of a 4-point. graph, but in this case, because this is not a 4-point graph, it's more complicated. I'm just calling it Y. So, but yeah, it's internal energy. KR T right, and then a difference of exponentials. K left T right minus D Y T. And here we have the blob. Okay. Okay, so this means that the wave function coefficient that corresponds to this graph is going to be equal to this factor this overall factor times and now you can, well, you can interpret which graph this integral correspond to, and it actually corresponds to a difference of graphs because of this minus sign. So this term will give you one graph, this term will give you another graph, and the graph is actually the following. So it involves the ball, of course, and then some lines running to the boundary. The boundary is here. But now the energy, so the sum of all of these energies is going to be KR, sorry, KR plus KL, just because we have KR here and KL here, okay? So, you know, these back to boundary propagators add up their energies, and we end up with a diagram with that sum, with that total energy flowing to the boundary. And then another diagram, which is very similar. Also, a number of lines running to the boundary. And in this case, the energy is KR plus Y. Okay, so this thing that I have drawn here is just basically the graph translation of this expression. And then we have this factor. Okay. So this is what I just wrote. It's written more beautifully. And let me look for a second to this denominator here, okay? So this denominator is y square minus KL square. Well, and this is just the sum of K1. Let me call, you know, this line here would be 1, then we have a number of lines until R, okay? So that's how I'm labeling them. So this Y is the energy that runs in this line. So it means that it's the magnitude of the sum of all of these momenta of all of these external lines, right? So then Y square is equal to this thing square, and KL is the sum of the energies of these many lines. So it means that it's going to be this sum of energy, and it has a square, so I squared. Okay. So this is equal to the to the product of this four momentum, KL. Okay, where KL is as a four momentum, it is, well, some of the energies in the zero component, and in the other, and in the spatial components, yes, this. Very good. So this is a product of the four momentum with itself. Yeah. So in other words, this is this. So why am I doing this? Why am I looking more closely to this denominator here? So these are wave function coefficients we are computing in the boundary, and then we don't have 4 momenta there because it's 3-dimensional. We just have special momenta under magnitudes. But I am constructing this artificial 4 momentum because I am going to relate this to the propagator of scattering amplitude, where there are 4 momenta. So I'm going to do that now. Move this here. Because notice that now in this diagrammatic expression here, if this graph has a singularity in KR plus K left, okay, just as the one that we saw before or similar, then sorry, what was it? No, sorry. Let me start again. if this bulb that we have here, which has energies K right flowing into it, has a singularity in K right, that means that this other bulb in which we have substituted the total energy flowing into it by K right plus K left is going to have a singularity in K right plus K left. Okay. So if the original thing has a singularity in K right, now this one is going to have a singularity in K right plus K left, which is the total energy of this graph. So this means that this graph, we have just proved that it's going to have a singularity in the sum of the energies, given that this one has a singularity in the sum of its energies. So it's a recursive it's a recursive thing what we have just proven. Okay, so if the bulb has a singularity in KR, then the whole diagram, which is this, has a singularity in KR plus KL. So I'm going to call total energy. So capital E is the sum of all of the individual energies entering the graph. Okay, so that is one thing, and the other thing is that if the residue of the singularity of this thing was the scattering amplitude corresponding to the process here, now the residue of this thing in this singularity is going to be the scattering amplitude corresponding to this thing. Why? Because we have the product of the scattering amplitude that corresponds to the bulb times this thing here, which is a propagator for flat space scattering amplitudes. Because as I just saw, is the K squared, the 4 momentum K squared. Okay, so if the residue is the corresponding scattering amplitude, then the residue of the whole wave function coefficient is going to be the corresponding scattering amplitude to the whole wave function coefficient, which I call AN. Okay. So what I have proved is basically a recursive relation that tells me that if this thing has a singularity and the residue is the scattering amplitude, then I can attach an external line to it and make a more complicated diagram in this way by attaching this line and attaching it to another vertex. And this whole thing will also have the same property, that it will blow up when we take the sum of the energies to 0, the external energies to 0. and the residue will be a scattering amplitude. And since we proved this explicitly for the simplest case, which is this contact interaction, we have proven it in general now for all tree-level graphs, because you can construct any tree-level graph by just attaching internal lines to other tree-level graphs, simpler tree-level graphs, in a recursive way. I don't know if that's clear. This was a bit, maybe a bit too fast. But well, let me write the conclusion, then I can ask for questions. So for all tree-level graphs, you know, in flat space, massless, etc. This. The limit of the sum of the energies that flow into the graph going to 0 is this. It's a singular limit. Sorry. It's a singular limit. The singularity is just a simple pole of the total energy, and the residue is the scattering amplitude. Are there questions? It's maybe not so important to follow all of the steps. It's just, I guess, important to understand that you can prove that if this thing has this property, basically this property, then the whole diagram also has it. And that you can construct any tree-level graph by starting from a contact graph like this one with any number of lines, and then attaching internal lines in this way, one after the other. In that way, you can construct any tree-level. So then, by proving this recursion, we prove it for all, and by proving it for the initial case, which is the contact diagram, we prove it in general. Okay, so this was, well, yeah, any question before I go on? Okay, if not, let's go on, because this was a very simple case. It was flat space, massless fields, scalars, etc. But similar arguments go through if you use spinning fields, etc. And in the sitter, also you can do a similar kind of argument, and it still works. And the reason is that the propagator, so you know, all of the things that I showed kind of depended on properties of the propagators, specifically properties of the propagators in the very early time part of the integral, which is where the singularity comes from. And the bulk to boundary propagator of the sitter well, remember it was a Hankel function of the second kind, so it was a complicated thing. But when we take the far past limit, the thing simplifies to something like this. So also to a plane wave. So this is very similar to the bulk to boundary propagator of the massless scalars in flat space that we saw. So that's why the thing still works in the sitter, because in that limit, the propagators look alike very much. For the bulk to bulk propagator, you also have a similar thing. You take the 2 times to the far past, then you have that the thing reduces to the to the flat space propagator for massless fields. So because in that limit the de Sitter case kind of reduces more or less to the flat space case, just with some factors of eta, we're gonna have a very similar expression in de Sitter. So for all the 3 level diagrams, this limit of the sum of the external energies going to 0 is going to be also a singular limit. The singularity is going to be this one, the energy to some power p, and then here we're going to have some factors of the magnitudes of the momenta. Okay, this is just, well, not so important, but you have some factors there of the momenta. You still have the scattering amplitude here as a residue, and probably the main difference is now that that the singularity is no longer a simple pole as it was in flat space, but now it has it's a higher order pole in general. Okay, and this number p, this power, well, it's given by a formula. This v is the vertices of the graph, the diagram. So you have to sum over all vertices, and you have to input here the mass dimension of the vertices. You know, you can have interactions with more derivatives or less derivatives. All of that is going to affect this power here. In general, if you have an interaction with many derivatives, with more derivatives, this number here will grow. Okay. So the singularity will be stronger the higher is the number of derivatives. So this is for the sheet. Okay, so this is the basic difference between the two, between flat space and the sitter, the order of the divergence. Okay. So very fast, the same thing happens, or very similar thing happens if instead of taking the sum of all of the external energies, you take the sum of the energies flowing into a subdiagram. So in this case, for example, for this very simple case, it would be K3 plus K4 plus S. I'm calling K3 the energy of this leg, K4 the energy of this leg, and S the energy of the internal leg. So this thing that yesterday we called E right, because it's the sum of the energies flowing into the right vertex. When this thing goes to 0, you're also going to have something similar, some divergence actually. So in flat space, the formula is going to be the following. So the limit when this sum of energies goes to 0 of this 4-point diagram is going to be a simple pole again of this sum of energies, and the coefficient of this simple pole now is going to be, well, the scattering amplitude of the right corresponding to the right vertex, okay, to the vertex that you are actually taking the sum of the energies off to 0, times the wave function coefficient corresponding to the other vertex left. Okay. And well, this still dies because this is not quite the wave function coefficient, but it's actually a specific combination of them. Okay. Oops. Okay, and in the sitter, the story is going to be very similar. The 4-point function is also going to be divergent in that limit, also with a power here which is not 1. In general, it can be higher power. And again, the product of the amplitude and the 3-point wave function coefficient. And in this case, in the sitter, just like it happened before, well, this amplitude comes with some powers of the of the momenta, of the magnitudes of the momenta in front of it. Not very important. And this also comes with some different powers. It comes with -1 to this power. Here, delta I is the scaling dimension of the field that runs in the internal line. Okay. And what I mean here with this tilde wave function coefficient that corresponds to this 3-point interaction is that here you have to write the corresponding wave function coefficient taking the internal energy to have a minus sign, okay? And then just the normal usual wave function coefficient with S being S. Okay, so of course, I've done it for the limit in which you take this sum of energies to go to 0, but the same thing happens if you take this sum of energies to go to 0. And then you would have the scattering amplitude corresponding to this vertex and the wave function coefficient corresponding to it. So basically a symmetric story. Okay, is there any question? Maybe a good reference for this is this paper by Benincasa, Arcani, Hamed, and Postnikov. So, okay, because this was a bit fast, maybe let me do let me make a bit of a summary of all of these singular limits. So if you take, okay, if you take the sum of the energies of lines that cut this blob, sorry, to 0, so the total energy K1 plus K2 plus K3 plus K4, if you take that sum to 0, you're gonna have a singularity which is going to be of this form, okay? You're gonna have a singularity of E to some power in the sitter, and the residue is going to be the corresponding flat space scattering amplitude. If you do the same for the energies entering here in this right vertex, so E right 0, in that limit you're going to have the scattering amplitude that corresponds to that vertex times the wave function coefficient that corresponds to the other vertex as the residue of a singularity also with some power in the sitter. In flat space, the power will be 1. Okay, so if you take E left, so the energy of the sum of the energies of the 3 legs going to 0, you have now the scattering amplitude corresponding to the left vertex times wave function coefficient corresponding to the right vertex, and then some power, singular. So this is the summary of these singularities for this 4-point case, okay? For more complicated diagrams, you will have more singularities. Yeah, well, notice that in the case of the sitter, this is not 1. This is just well, another power, which will depend on the dimension of the interaction, etc. As I said, you can easily know what is that power by doing dimensional analysis. So counting the dimensions of this, and this, which you know, and then you can tell what is the power of that singularity. And 2 very important things about these singularities is the first one is that the singularities do not correspond to physical momentum configurations. Okay, so if you measure this 4-point correlator, let's say, for example, in the sky, as I was saying, you cannot tune the variables such that you access the singularities. They do not happen for physical momentum. They happen for well, they happen if you take your wave function coefficient and you analytically continue to complex momenta. Okay, so they do not correspond to physical configuration. And this is very easy to see because in order to access the singularities, you need to take a sum of energies to be zero. But energies, magnitudes of momenta are positive, right? For real momenta. If you want to have a magnitude of a momentum which is negative, you need to analytically continue to complex momenta. So for physical configurations, you will never get a sum of positive thing of magnitudes to be zero. And the other important thing is that, well, requiring correlators to have these singularities is going to be a very powerful tool to fix them. We are not only going to require them to have these singularities, but we will also require them to not have all singularities in physical configurations. Okay. So if you give me if you give me a correlator which has, for example, the one we computed yesterday for 4-point massless scalars in flat space, this one has these 3 singularities. So this one seems to be okay. But if you give me a correlator which instead of this has E right, and then instead of having E left, which is K12 plus S, has K12 minus S, this singularity can be accessed by physical momenta because it's just the difference between 2 positive things. So this is not good. This we are not gonna like it. Okay, this means that this correlator is not, this wave function coefficient, sorry, is not valid. It has a problem. So we will require also absence of other singularities. So these 2 things, the presence of these singularities with these residues and the absence of other non-physical singularities, are going to be tools that we are going to use to fix correlators, and they are going to be very, very powerful. Okay. In a way, the strategy is going to be, okay, we know that the wave function coefficients that we are interested in have these limits, these divergent limits, and we know their values are on these limits because we know the residues. So the general strategy is going to be how to extend the function away from these limits to get the actual complete function for general kinematics. Okay, that's going to be the challenge, and we're going to use some other input, some more tools to try to do that. But we will rely very heavily on knowing the singularities always because it's very useful. Okay, I'm not sure if this whole thing about the singularities was clear. Is there any question? I'm gonna do an example now, so hopefully that will make things easier. Okay, so the example is, this one is massless scalar in flat space, so the wave function I just wrote. Not sure if I should do this one or wait until the example I'm gonna do in the next section. Maybe it's useful to go to the next section. In the next section, I'm going to talk about word identities. And one thing I will do is I will, in the example, I will compute one correlator just by using one correlator, no, sorry, one wave function coefficient just by using the knowledge of these symmetries, singularities, and then I will do something related to the word identity. So I think it should be clear with the example. Okay, so very good. So word identities. Okay, so now consider that we are studying a theory, a setup in which we have massless spinning fields. Okay. So that means that the wave function of the universe is going to depend on these massless spinning fields. And for example, I'm going to write here just a graviton, a vector, and the scalar also. The scalar doesn't need to be massless, but okay. Let me actually specify that this is a graviton. This is, for example, a gluon or a photon. Yes, vector. This is scalar. So, you know, these fields, gluons, photons, gravitons, have some gates transformations, right? And the gauge invariance of the wave function of the universe, so the gauge invariance of our observables and so on, is going to imply some identities on the wave function coefficients. Okay. So gauge invariance of this object is going to imply some identities. So for example, for the case of the vector, the gauge transformation, if we take, for example, a gluon, okay, the gauge transformation is going to have this form. And so the gauge parameter is this lambda. The gluon itself transforms in that way, and then we have a bunch of scalars that we are labeling with that label small a. The gauge transformation is going to be something like this, okay? So this is the scalar. Let me make it. Oops. And this is the vector field. Okay. Now this, if you try to find the variation of this functional with respect to this gauge transformation, well, you will find an expression. It's not very important, but it's going to be this. What's this? Plus over the function. And if we require this wave function of the universe to be gauge invariant, so invariant under this transformation, this has to be 0, okay? So this condition implies, if you then take functional derivatives of this thing and so on to compute the correlators, this implies that the contraction of the momentum of this field, vector field, of this gluon field, with a correlator in which this field is present, with some other scalars or whatever fields you have. Well, it is a bit. There's an index proliferation here, but this is going to be given by a sum of correlators that involve only the other fields that are, for example, scalars. So this is going to be K2, this is Ka plus K1, this is Kn, okay? And well, I'm going to omit this scalar indices, but well, the scalar indices should also be there. Okay, so this is so what we call it word Takahashi identity. Okay, it's a word identity for the correlators for these wave function coefficients actually. That comes from the gauge invariance of the wave functional of the universe under this gauge transformation. Okay, so this is a constraint that this wave function coefficient will have to satisfy. Similarly, you can get from diffeomorphism invariance, you can get a similar thing. Okay, if you impose that the wave function of the universe is invariant under diffeomorphisms, you're gonna get similar word identities. This time for the for correlators involving the tensor, the spin-2 tensor. Okay, the dual field to the graviton. And the structure is going to be very similar. Something here, correlators of the other fields. Okay. This psi here is a polarization vector. So we have fields with spin, so that means that the correlation functions will have polarization vectors with them. Okay. Okay, very good. So, well, it's not very important to know what is the structure of these word identities. What is important is that these word identities reflect locality of the bulk physics. Okay, so they are a consequence of, well, this gauge invariance and this diffeomorphism invariance of the physics in the bulk, in the sitter or flat space or whatever. But they are consequences on the observables that we are computing in the boundary. Okay, so we are translating some principles of the bulk physics into conditions of these objects in the boundary. Yeah, and the principles are, as I said, these invariances and locality of the bulk physics. And these word identities lead to constraints which are very strong on these objects, on the wave function coefficients. And we are going to see that in an example. Okay. Yeah, let me go to the example. I think it will be useful. So the example is going to be this wave function coefficient. It's a 4-point wave function coefficient, which involves one massless spin one field, J, which is this wiggly line, and conformally coupled scalars in the sitter. So these conformally coupled scalars are just so this conformally coupled scalar var phi, it's a field which has this mass in the sitter. Okay, so it's not a massless field. For the first time, we are not computing graphs of massless scalar fields, and it has a property that is conformally coupled, in the sense that well, this mass implies that the theory has a conformal. The theory of this field has a conformal symmetry, is conformally invariant, and because the sitter is conformally flat, the theory of this field, free field in the sitter, is equivalent to a massless field in flat space. That's why it's called conformally coupled. And well, the fact that the field has this mass implies that the scaling dimension of the dual field, remember that it's given by this formula. So if you plug in the mass here, this is going to give you that the scaling dimension of the dual field is 2. Okay. And for J, we can also compute the scaling dimension of this field, which is the dual of photon, graviton. This is a massless field of spin 1. So the formula is this one, and the conformal dimension is also 2. Okay. So yeah, we want to compute the wave function coefficient corresponding to this graph. The way we are going to do it is by imposing that it satisfies those singular limits that I talked about just a moment ago. Okay, the 3 of them. Actually, no. Actually, it will just be enough to impose 2 of them. We will not impose the total energy one. So in order to do that, we need to first write the 3-point information, right? Because remember that the residues were given by the 3-point information. So let me start by writing the 3-point information. So on the right vertex, we have a coupling between 3 conformally coupled scalars. Okay, the scattering amplitude of 3 scalars is just 1. The scalars are massless and so on. On the left hand side, we have a 3-point vertex of spin 1 massless field and 2 scalars, and this, the corresponding scattering amplitude is very simple. It's just this, where these are 4 momenta because this is a scattering amplitude. Okay. K2 is just the moment. Sorry, these are 4 vectors. K2 is just the momentum of one of these scalar legs, and psi1 is the polarization vector of the spinning field. Okay, those are very simple. And then the wave function coefficients that correspond to this, the wave function coefficient that corresponds to this interaction here is, well, it's a bit exotic because it involves a log. That is because, well, we are doing the computation in the sitter, and we are doing it for this conformally coupled scalar. And conformally coupled scalars in the sitter, when they have this cubic interaction, the corresponding object has a logarithm. It solves the conformal word identities anomalously. It's a bit of an exotic story, but and for the other vertex, this one here, we have that the wave function coefficient is this, and this time these are 3-dimensional vectors because now we're talking about wave function coefficients. Okay. Notice that this 3-point wave function coefficient is very easy to see that when you take the limit of the 3 energies, of the sum of the 3 energies to go to 0, you get the singularity that you would expect. This one, and the residue of this singularity is 2 times this, which corresponds to the flat space scattering amplitude. Okay. So for this diagram, things work, and actually also for this one, because the coefficient of this singularity, which in this case is a logarithm singularity, it's 1. So it's also the scattering amplitude of the corresponding process. Anyway, yeah, so now we are going to use Yeah, we're going to use these two singularities, this one and this one. Okay, we are going to impose them on our correlator. In order to know the order of these singularities, we need to do some power counting. And in particular, we need to know what is the dimension of the energy dimension of this wave function coefficient that we want to compute. Notice that I am writing this little s here, and the reason is that we're computing basically an S channel diagram, right? K1 and K2 are a couple here, and K3 and K4 are a couple here. So that is what this little s means. Later on, we will see that we will need to introduce T and U channel as well. That's going to be the nice thing about this example. Okay, so the mass dimension of this object is given by the scaling conformal word identity that I talked about yesterday. Well, actually, I'm not gonna. Well, it's just the sum over the 4 fields. This is the scaling dimension of the 4 fields, and this just comes from the fact that we are computing a 4-point wave function coefficient. So the 4 fields have scaling dimension 2, as you can see up here. So the result is -1 for the scaling dimension of the whole object. Okay. Okay. The reason why we have to know this, as I said, is that this will tell us what the order of the singularity is. So let's impose the singularities. So when the energies entering the left vertex go to 0, we have that this object needs to factorize in these 2 objects, and it needs to have a simple pole. Okay. Yes. Mass dimensions, power counting tells you that it needs to be a simple pole. So with this information here of the this and this information, we can write what this residue is. So it's going to be just the scattering amplitude over L. I'm just substituting the expression for the tilde wave function coefficient, which is a difference of the wave function coefficients evaluated at slightly different energies. And now if I substitute explicitly from the previous slide, I get this. This logarithm comes from the fact that this 3-point wave function coefficient is a log. Okay, so we know that in this limit, our 4-point wave function coefficient needs to take this value. Let's do the other limit. In this case, we do power counting, and we realize that the divergence in this case needs to be a logarithmic divergence, actually. Yeah, and we have this. And well, we do the same. We plug in the information from the previous slide, and we get this. 11. let me remind you that when I write K12, I mean sum of K1 plus K2. When I will write K34, I mean this. It's just a faster way to write these things. Okay, so we need to find a function that in these two limits it goes to these values. Okay, and we can see that there are some common structures, so it's probably not going to be hard. Like we have this vector structure, we have the E-left singularity, we have the E-right logarithmic singularity, etc. So it's not hard to guess a function, to just write a function that correctly factorizes in these two limits. For example, if you think about it for like 30 or 40 seconds, you could easily find that this function is an obvious candidate, okay, because it factorizes correctly in both limits. By the way, here I introduced this mu. This mu is just, well, it can be it can be actually some energies or something. It's just parameterizing the fact that we don't know what else is in this logarithm multiplying the sum of these energies. So, well, this could be anything. And because we have this other logarithm in the other limit, well, it's very natural to just say, okay, this mu, I'm going to take it to be K34 minus S. Okay, so this is a possible function. This is a possible thing that could be the correct wave function coefficient. But we said we are not quite there yet, because we said that we didn't like this kind of singularities, singularities in this configuration or in this configuration, because these are physical configurations. You can access them for physical values of the momenta, and we don't like singularities for physical values of the momenta. Okay, what does it mean for something that I can measure to be singular? Can I measure a singular thing? Is that physical? So we will demand them to be absent now. Okay. Okay, so to get rid of this K34 minus S, we can do one thing. Let me think how to write this. Okay. We want to get rid of the singularity, okay? And in order to do that, well, this K34 minus S is here because we saw it in this logarithm, and then we thought, okay, maybe we can just write it here in our final answer. But notice that in this limit, we can reinterpret this K34 minus S in the limit in which E left is 0. The fact that E left is 0 means that S is minus K12. So this can be rewritten as K12 plus K34 in that limit. And this is the total energy, right? So, well, we could just reinterpret this thing as E in this limit. It's totally valid. So then we can say that maybe the correct wave function coefficient. Let me keep the sign. Maybe the correct wave function coefficient is just the same, but with an E instead of that ugly limit, ugly singularity. And in this case, we have got rid of that singularity when K34 minus S goes to 0. So that's good. But we still have this one, right? But notice that in the limit in which goes to S. So in the limit in which this thing goes to 0, the actual object, the full object, is not singular, because in that limit, this thing becomes 1. Okay, you can see it. You can see it easily, and then the limit is regular. So we don't have a singularity that we don't like. So we don't have a singularity that we don't like, and we have that this object factorizes correctly in the limits that we want it to factorize. So this is the correct answer. There's one further check to do, which is that the singularity when the total energy goes to 0 is the correct one, and you can actually check it, and it is. So this thing is the correct answer. We have reconstructed this function, this wave function coefficient, from just knowledge of its singular points. Okay. Is there any question now before I do the next thing? Okay. Yeah, the next thing is then to use these word identities. So in this case, because we are working with a vector, we will use this one, the equivalent to this one. And what we're going to see is something very beautiful. We will see that. Actually, I don't know if I should go in a lot of detail because I don't have so much time. But okay. Anyway, what we will see is that this satisfying this word identity will require us to add the other channels as well. Okay, the T and the U channels. Otherwise, the whole thing will not be consistent. So the word identity, schematically, if you write it for this specific wave function coefficient, the word identity is this one, minus E3. By the way, yeah, 2, 3, and 4 label the scalars. Yeah, so here we are evaluating the scalar at the sum of the momentum of the scalar itself and the vector. Here the same thing for this scalar, and here the same thing for this scalar. And then we have some E here, which is kind of, it corresponds to the coupling of this J, of this vector field to the different scalars, okay? That's why they're called E2, E3, E4. Okay, very good. So this is just what the word identity is. So if we substitute the knowledge that we have about this wave function coefficient, we get this. Oops. 834 plus S for mu. Remember that this wave function coefficient was a logarithm. This U is the U channel equivalent to S. So U is K1 plus K, this thing. And then we also have a T, which is this thing. 2, 3 plus T. So this is the word identity. So now what we can wonder is, does our solution here satisfy it? So if we take we just contract this with K1, does it satisfy this word identity? And the answer is no. well, the details about how to do that, about how to contract, about how to compute this, plugging in our result here. I'm not going to give you the details because it would take too long. It involves using spinor helicity variables and so on. But well, let me just tell you the result. Maybe the next slide. So this is the result that we computed before. This is some normalization that I am adding, just random normalization. Before plus S over total energy. Okay. So you can see that this thing here, well, this does not coincide with this, no matter which values we take for the E's or whatever. This just does not satisfy the word identity. So this is not consistent with the word identity. And well, it's obvious from looking at this word identity here that we might have a chance to solve it if we add the T and the U channels, right? Because we have some T and U channel quantities appearing there. So that suggests that we have to add these channels. So that is what we will do. So this is the S channel that we computed, and we can just add the T and U channels. Because of the symmetry of the problem, the symmetry of the graph, these T and U channels are just going to be given by permutations of the result that we have. So the result of doing that, S plus T plus U, so all of the three channels. The result is now going to be this thing that we had already here on the S channel. Minus this thing on the channel. Minus same thing for the U channel. Minus this. Okay. And this expression is only consistent with this expression if you do the following. If you take this normalization that I added, ES to be equal to 2, ET to be equal to E4, EU to be equal to E3, and, very important, if you have the sum of the three couplings to be 0. So this is charge conservation, right? So basically what we have done is, from imposing these word identities, which are the boundary manifestation of some bulk physics, by imposing them on the boundary objects, on these wave function coefficients, we discover that the whole thing is only consistent if we have charge conservation. So we cannot have a consistent theory in which these three scalars have charges that don't add up to 0. So we cannot have a process in which the total charge is not conserved. So this is very nice. We have bootstrapped this fact basically. So we have found this consistency condition for our theory. So this was just one example, but similarly, one can show many other things, many other cool things. For example, one can show if you study other different 4-point graphs, you can show that a theory in which gluons coupled to scalars is only consistent if this condition is obeyed. So if the couplings of the scalars to the gluons transform in a representation of the algebra. Similarly, one can also prove the equivalence principle. So in other words, by studying similar 4-point graphs that involve gravitons, you can prove that all scalars need to couple with the same strength to the graviton. You can also prove that if you have several gravitons in the game, the gravitons also couple to gravitons with the same strength. So the coupling to gravity is universal. You can prove that by playing the same game as we just did. You can also prove the Jacobi identity for these structure constants. Okay, if you have a 4-point wave function coefficient which is all gluons, you can prove that they need to satisfy the Jacobi identity. Their couplings need to satisfy the Jacobi identity. You can also prove that massless fields with spin 3 or higher cannot couple to matter in a consistent way. You can try to write a wave function coefficient for one of these massless higher spin fields and try to make it consistent with the 3-point information and so on, and you will see that you cannot couple it to scale. So this is a list of examples of things that we did using this. So it's very powerful. It really restricts a lot kind of theories and interactions that you can have, and it's all from a boundary perspective. So it's pretty cool. Questions here before I go to the next thing? Okay, good. So, well, I still have too many things, so I will not finish everything that I have here in the script. So, what should I do? I will try to be fast and just give an impression of what comes in the next section. Let me see. Yeah, okay. Very good. So the next section is about unitarity and what unitarity of the physics in the bulk implies for these wave function coefficients. And we'll see that it's also very powerful. It also implies a set of rules for these wave function coefficients, and that they can be used to bootstrap them. So, okay, let me go directly to this slide and tell you that so some properties of the bulk-to-bulk some properties of the bulk-to-bulk propagators. Sorry, I'm trying to think about what to omit. Plus unitarity imply the following relation for 4-point wave function coefficients in flat space. So properties of the bulk-to-bulk propagators plus unitarity implies that if I add up the 4-point wave function coefficient and a slightly deformed 4-point wave function coefficient, which is just the usual one with the complex conjugate and with the external energies taken with a minus sign. So if I take that sum is equal to minus 2s times the product of the 3-point vertices corresponding to these two vertices of the 4-point function. With this tilde, that remember that implied some difference of the two wave function coefficients, etc. So this is the this is the mathematical formulation. Let me repeat here what this was. This. Yeah. 1/2s. Okay, and S, remember, is the energy of the internal line. Okay, so that is a mathematical expression. Schematically, what this implies is this thing that I draw here. So here we have the 4-point object. Here we have this slightly changed 4-point object, which is complex conjugate, and then the external energies have a minus sign. And on the other, on the right-hand side of the equation, we have this thing, which you can kind of interpret as the fact that we are taking the internal line and we are cutting it. Okay, and by cutting it, we are taking this, well, this line. We are taking the two lines to the boundary. Okay. So this is for flat space, but again, the thing kind of generalizes well to the sitter. And in the sitter, we have a very similar expression. Actually, the left-hand side is the same. It's just that in the right-hand side, you have a power spectrum. This is the 2-point function of the field that runs in the internal line. Okay, so just a minor modification. The spirit of the rule is the same. This is the so-called cutting rule or cosmological optical theorem, and this was found by these two papers last year. Yeah, so the first one was by Enrico Bayer, Harry Goodhue, and Sadra Yassayeri, I think. Yes. This other one was by Scott Melville and Davis and Sebastian Cespedes, and they were kind of simultaneous. Yeah, and this cutting rule can actually be written even in a more general way for any wave function coefficient. And then on the right-hand side, well, the left-hand side is the same as before, but in the right-hand side, you just have a sum of all possible cuts that you can do to the diagram. Okay. So this is cutting rule. Anyway. And in here, I draw an example. So for example, for this more complicated wave function coefficient, you will have that in the right-hand side, the sum of cuts that you have to do is this one. Cutting all of the 3 internal propagators and then cutting sets of 2 and then cutting the 3 of them. If you want to learn more about these more complex cuts, there is this paper by Enrico Bayer and Scott Melville. Yeah, and this is very powerful because, as you can see, it relates complicated graphs to simpler graphs, because for example, this graph no longer has a loop. This one has a loop. This one no longer has a loop. And you know, and some of them have well, in this one, for example, you just have the product of some diagram here with some other one here and some other one here. So you're relating, you are decomposing kind of complicated graphs in terms of simpler ones, which is very nice. And this can be also used to bootstrap a lot of wave function coefficients. The nice thing about these rules is that they know not only work for the sitting and flat space, but you can also formulate them for a general F-LYR spacetime or fields of different characteristics, different masses, etc. So yeah, they are quite powerful. Yeah, let me mention that these people, the group of Enrico Baggier in Cambridge, they have bootstrapped a very large number of correlators with using these rules and some other stuff. So yeah, it's really useful. Okay, here I had an example. I just wanted to test this rule for the simplest case that we have done many times, but I think it's obvious you can do it in 2 minutes in your when you have a moment. So I'm not gonna look at it. I think I should finish soon. So I think I will just quickly go through this final section, which I will just explain the spirit of it. I had a very long example here, but which I knew I wouldn't be able to do anyway. And then I will go to the end. Okay, so in this part, I just wanted to tell you about some energy deformations that we do to the wave function coefficients. So for example, you can take some of the energies and shift them by a complex number set. You can take also some of the internal energies, for example, this, and also shift it by this complex number, so this set. Okay. This means that now your wave function coefficient will also be a function, of, well, still all of the momenta, but also of this set complex number. Okay. This is inspired, by the way, in the BCFW recursion relations of scattering amplitudes, if you know about this. BCFW is exactly what I'm going to explain now, but for scattering amplitudes, and it was done some years ago. So then, this wave function coefficient, the original one that I'm interested in bootstrapping, in computing, is just this thing evaluated at 0 with no deformation. And I can express this as a complex integral, right, of this function. So this function has a pole at z equals 0. This is the complex set plane. So there is a pole here at z equals 0. So if I do an integral around this pole in the contour C, this is going to give me just the residue of this pole. And the residue of this pole is just the wave function coefficient that I want to compute without the deformation, right? So this means that this object that I'm interested in can be related to the sum of the residues at the other poles by doing a deformation of this contour, right? I just take this contour and I deform it away, I push it to infinity, and then I pick all of the other possible poles that this psi of z has. And all of these poles are going to be related to the singularities that I mentioned before in the sums of energies. So this means, in mathematical terms, that this is going to be my object of interest is going to be the sum of the residues at these zj's here. Residues of this function plus a possible residue at infinity. Okay, we might have a boundary contribution from the fact that we are pushing the contour to infinity. That's important to keep in mind. So if we look at our old friend, the 4-point wave function coefficient of massless scalars in flat space, and we do this shift, for example, this is just a very simple example. We're going to get this as a shifted function, right? The reason is that this E is the sum of all of the energies, so it involves a K1. So it's going to pick this shift. This EL also involves K1, so it's also going to be shifted. And E right does not involve K1, so it's not shifted. And this shifted wave function coefficient will have poles at Z equal minus E and minus EL, right? And the residues of those poles are going to be given by the scattering amplitudes and the factorization conditions that I mentioned before. So this means that with that information about the lower point wave function coefficients and scattering amplitudes, we can reconstruct the whole function by using this formula. So this is also quite interesting. And of course, this works better for flat space wave function coefficients because they have just simple poles. So these residues are really easy to compute. In the de Sitter case, you have to do more work because the poles are higher order. You have a whole Lorentz series entering here. But it's a powerful method, and yeah, it's inspired directly by the scattering, the story for scattering amplitudes. Okay, yeah, I had a very long example here, which obviously I cannot do, so I'll just go to the last section, and then I will conclude. Yeah, I will try to do that in 5 minutes. So here in others, I'm just going to mention some other tools to bootstrap. One is the so-called manifestly local test. So I will just say that manifest locality of the interactions of the dynamical fields of the wave function coefficient implies this nice condition for the wave function coefficient, and this can be used to bootstrap it also. And you can learn more about this in this paper. It was by again Pajer, Yasayeri, and David Stefanison. Also, it has been also very useful for them to bootstrap a lot of wave function coefficients. Another is soft limits, in the sense that shift symmetry of the interaction implies, just like for scattering amplitudes and so on, implies that you have an Adler zero or a vanishing soft limit kind of thing. So if you have a field which enjoys a shift symmetry, and if you have one of those fields in one of the wave function coefficients, one of the conformal correlators that you are computing, if you take the limit in which its momentum goes to zero, you should get a zero. You should get a vanishing result as a consequence of the shift symmetry. And this can also be useful to fix wave function coefficients when you need some extra input, some extra information. And then in our last paper this summer, we also introduce a number of transmutation operators, that's how we call them, which takes you from a flat space, wave function coefficients to the Sitter one. So these are operators that are differential or integral, differential and integral operators, and you feed them a flat space a flat space wave function coefficient, which are in general simple. They only have simple poles, etc. They are easy. You feed it, and it gives you the corresponding de Sitter wave function coefficient for the same process. And this is very nice because the de Sitter ones, as I have said many times, are more complicated. So it's a nice tool. Okay, so these are all the methods I wanted to talk about. So I just have a final outlook slides actually. I just wanted to emphasize that this cosmological bootstrap I've been talking about has connections to many fields, to many different things. Observations, because it's related to bootstrapping the correlators that are the initial conditions for the correlators that we observe today. Inflation, because these correlators are a window to the inflationary dynamics. We can try to learn from them about the inflationary dynamics. And in this sense, this cosmological collider, this fact that very energetic, very massive particles could have been produced during inflation that we might measure thanks to these correlators. And then the study of these correlators has connections also with CFTs, because the symmetries of de Sitter, so the approximate symmetries of inflation, translating to conformal symmetries in the boundary. And this, of course, has a holographic flavor, right? There is, as you could see, probably many of the notions that I used are familiar from ADS-CFT and so on. And then many of the methods that we use are inspired by the study of scattering amplitudes, because the bootstrap was very useful in that context. So yeah, it has many connections. And let me finish with this slide. So I just wanted to say that we have a very, very precise understanding of what the physics of the bulk in ADS means for the observables in the boundary. We have non-perturbative formulation for the rules that those objects satisfy. In the case of Minkowski space, we have the S matrix, scattering amplitudes. Something enters, scatters, and then goes away. And we also have rules, and we have an understanding of what these objects satisfy. At tree level, we understand them fully, and then at loop level, we have a good handle. And however, in de Sitter, which is the closest situation to the real world, because our universe expands, and it expanded in the past even more. In de Sitter, we have a very, very low understanding. We are just starting to understand things at tree level, as I showed in these lectures. So it's very frustrating that the closer we get to the real world, the less we understand. So this is a motivation to keep on working on these things. And there are many challenges ahead. Try to find a non-shell formulation for these things, something similar to the Park-Taylor formula I showed yesterday for function coefficients. Try to find non-perturbative rules. Everything I said was perturbative. Try to find what is the implication of causality for these objects, causal physics in the bulk. How does this translate to the boundary? Trying to find maybe we can do things similar to the positivity bounds of EFTs, but for these objects in de Sitter. Well, do they obey double copy between gauge and gravity theories? What happens with loops? I have barely mentioned loops. We don't know much about them. What is the UV completion of these objects, etc. So many things. Yeah, and with that, I will finish. Sorry for going, so but well, a bit over time. Thank you.
Thank you, Carlo. It was very nice lecture. Are there any questions?